You turn a key, or you press a button, and a dead machine made of metal, rubber, and plastic suddenly comes alive. It shakes slightly, it hums, it vibrates through the steering wheel into your hands, and then you drive to work without thinking about it for a single second. You've done this 1,000 times, maybe 10,000 times, and you have no idea what just happened. You don't know what's going on under the hood. You don't know why the engine makes noise. You don't know why it needs oil or coolant or gasoline or air. You don't know why it gets hot. You don't know why it eventually dies. You just know it works until it doesn't. And then you hand a mechanic your credit card and try not to cry. Most people go their entire lives driving cars without understanding the basic machine that makes them move, and that's fine. You don't need to understand how a refrigerator works to eat cold food. But here's the thing, your refrigerator doesn't cost $7,000 to replace when it fails. Your engine does. And a huge percentage of engine failures are preventable if you understand even the basics of what's happening inside it. So here's the deal. No engineering degree required, no jargon without an explanation, no diagrams you need a PhD to read, just a clear, honest explanation of how the thing under your hood actually works, from the first spark to the last mile. By the end, you'll understand your engine better than most people who've been driving for decades. Let's go. Your engine is an explosion machine. That's the fundamental concept. Everything else is details. An internal combustion engine works by burning fuel inside enclosed cylinders and using the force of that combustion to push pistons, which turn a crankshaft, which eventually turns your wheels. The word internal in internal combustion means the burning happens inside the engine, as opposed to external combustion engines, like steam engines, where the fuel burns outside and the heat is transferred in. The fuel is gasoline. The other ingredient is air, specifically the oxygen in the air. When gasoline vapor mixes with oxygen and is ignited by a spark, it burns rapidly. That rapid burning creates an enormous expansion of hot gases. Those expanding gases need somewhere to go, and the only direction they can go is down, pushing the piston toward the bottom of the cylinder. That downward push is the engine's power stroke. That's where motion begins. Think of it like a cannon. You pack gunpowder into a tube, light it, and the explosion launches a cannonball. Your engine is doing the same thing, except instead of launching a ball, it's pushing a piston. And instead of doing it once, it's doing it thousands of times per minute in a controlled, precisely timed sequence. Your engine is a cannon that fires continuously and converts the force into rotation instead of projectile motion. Every single component in the engine exists to support this one process. Get air and fuel into a cylinder, compress it, ignite it, extract the energy, push the waste out, and do it again, over and over and over, thousands of times per minute for years. That's the engine's entire job. The vast majority of car engines on the road today are four-stroke engines. That means each cylinder goes through a cycle of four distinct movements, 4 strokes of the piston to complete one power cycle. These 4 strokes are intake, compression, power, and exhaust. They happen in that order, every time, in every cylinder. This sequence is the heartbeat of your engine. Once you understand it, you understand the engine. Stroke 1 int. The piston starts at the top of the cylinder and moves downward. As it descends, it creates a vacuum, a low-pressure area inside the cylinder. The intake valve opens, and air mixed with fuel is drawn into the cylinder through the intake port. Think of pulling back on a syringe. The plunger goes down, and fluid rushes in to fill the space. The piston is the plunger, the air-fuel mixture is the fluid. By the time the piston reaches the bottom, the cylinder is filled with a precise mixture of air and vaporized gasoline. Stroke 2. Compression. The intake valve closes. The cylinder is now sealed. Both valves are shut. The piston reverses direction and moves back up, compressing the air-fuel mixture into a smaller and smaller space. By the time the piston reaches the top, the mixture has been squeezed to roughly 1/10 of its original volume. That's a compression ratio of about 10,001, which is typical for a modern gasoline engine. Compressing the mixture serves 2 purposes. It concentrates the fuel and air molecules closer together, which makes the combustion more powerful, and it raises the temperature and pressure of the mixture, which helps it ignite more completely. Imagine squeezing a balloon with both hands. The air inside gets hotter and the pressure goes up. Same thing is happening in the cylinder, except the balloon is a steel cylinder and the air is laced with gasoline. Stroke 3. Power. This is the money stroke. The piston is at the top. The compressed mixture is primed. The spark plug, a small electrical device threaded into the top of the cylinder, fires a precisely timed spark across its electrode gap. That spark ignites the compressed air-fuel mixture. The mixture doesn't explode all at once. It burns rapidly in a controlled flame front that sweeps across the combustion chamber in a fraction of a millisecond. The burning gases expand violently, and that expansion drives the piston down with enormous force. This downward force is transferred through the connecting rod to the crankshaft, converting the linear motion of the piston into rotational motion. This is the only stroke that produces power. The other 3 strokes are setup and cleanup. Stroke 4. Exhaust. The power stroke is over. The combustion gases, now spent, mostly carbon dioxide, water vapor, and other byproducts, are still in the cylinder. The exhaust valve opens and the piston moves back up, pushing the spent gases out of the cylinder through the exhaust port and into the exhaust manifold, which routes them through the catalytic converter, the muffler, and out the tailpipe. Once the piston reaches the top and the cylinder is purged of exhaust gas, the exhaust valve closes, the intake valve opens, and the whole cycle starts again. 4 strokes: intake, compression, power, exhaust, suck, squeeze, bang, blow. That's the mechanic's shorthand, and once you hear it, you'll never forget it. Every cylinder in your engine repeats this cycle continuously, thousands of times per minute for as long as the engine is running. One complete 4-stroke cycle requires 2 full rotations of the crankshaft, 720 degrees. At 3,000 RPM, a moderate cruising speed, each cylinder is completing 1,500 power cycles per minute. That's 25 explosions per second in each cylinder. In a 4-cylinder engine, that's 100 explosions per second across all cylinders. In a V8, it's 200. Your engine is a machine gun of controlled combustion events happening so fast that it blurs into a smooth, continuous hum. What sounds like a steady engine note is actually hundreds of individual explosions per second, sequenced so precisely that they overlap into perceived smoothness. Let's meet the major components. Each one has a specific job, and understanding what it does helps you understand why it fails and how to prevent that failure. The block. The engine block is the foundation, a massive casting of aluminum or cast iron that contains the cylinders. The cylinders are the tubes the pistons slide up and down inside. The block also contains passages for oil and coolant to flow through. It's the skeleton of the engine. Everything else bolts to it or lives inside it. The pistons, cylindrical plugs, usually made of aluminum alloy that slide up and down inside the cylinders. Each piston has rings, metal bands that seal the gap between the piston and the cylinder wall. The rings serve 2 purposes. They prevent the high-pressure combustion gases from leaking past the piston into the lower part of the engine, and they scrape oil off the cylinder walls to prevent it from entering the combustion chamber and burning. Piston rings are one of the most critical sealing components in the engine, and when they wear out, you get low compression and an engine that burns oil. The connecting rods. These are the links between the pistons and the crankshaft. Each piston is attached to a connecting rod via a wrist pin. The other end of the connecting rod attaches to the crankshaft. The rod converts the piston's up and down linear motion into the crankshaft's rotational motion. Connecting rods take enormous stress. They're under tension, compression, and inertial loads thousands of times per minute. A broken connecting rod is one of the most catastrophic engine failures possible. It often punches a hole through the side of the engine block, which is both violent and extremely expensive. The crankshaft, a heavy, precisely machined shaft that sits at the bottom of the engine block. It is offset journals, the crank pins, where the connecting rods attach. As the pistons push the connecting rods down, the offset design of the crank pins converts that push into rotation. The crankshaft is the output of the engine. Its rotation is what ultimately turns the transmission, the drive shaft, and your wheels. The crankshaft is balanced with counterweights to smooth out the inherent vibrations of the pistons firing at different times. An unbalanced crankshaft vibrates destructively. A well-balanced one spins smoothly for hundreds of thousands of miles. The cylinder head. This bolts to the top of the engine block, sealing the tops of the cylinders and forming the combustion chambers. The head contains the intake and exhaust valves, the valve springs, the camshafts in overhead cam designs, and the spark plug holes. The head is where the intake and exhaust ports are cast, the passages through which air comes in and exhaust goes out. It's a complex, precision-machined piece that handles extreme heat and pressure. The head gasket, a thin but critical sealing layer between the engine block and the cylinder head. It seals the combustion chambers, the oil passages, and the coolant passages simultaneously. A blown head gasket, one that fails to seal, allows coolant to leak into the cylinders, oil to mix with coolant, or combustion gases to escape into the cooling system. A blown head gasket is one of the most expensive common engine repairs because accessing it requires removing the entire cylinder head. The valves, metal discs that open and close to control the flow of air-fuel mixture into and exhaust gases out of each cylinder. Intake valves let the mixture in, exhaust valves let the spent gases out. They open and close thousands of times per minute with millisecond precision. The timing of when each valve opens and closes, relative to the piston's position, is critical for engine performance and efficiency. The camshaft, a shaft with egg-shaped lobes that physically opens the valves as it rotates. Each lobe corresponds to one valve. As the camshaft spins, the lobes push against the valves, either directly or through rocker arms and lifters, forcing them open against their springs. When the lobe rotates past, the spring pulls the valve closed again. The shape of the cam lobe, its profile, determines how far the valve opens, how long it stays open, and how quickly it opens and closes. Aggressive cam profiles open the valves farther and longer, allowing more air and fuel in for more power. Mild cam profiles prioritize smooth idle and fuel efficiency. The camshaft is driven by the crankshaft through a timing chain or timing belt, ensuring the valves open and close in perfect synchronization with the pistons. The spark plugs, small threaded devices that screw into the cylinder head, one per cylinder. Each spark plug has an electrode at its tip that creates an electrical arc, a spark, when the ignition system sends a high voltage pulse to it. That spark ignites the compressed air-fuel mixture at exactly the right moment. The timing of the spark is controlled by the engine's computer and adjusted continuously based on engine speed, load, temperature, and other factors. A spark that fires too early causes knock, premature combustion that hammers the piston before it's in position. A spark that fires too late wastes energy because the piston is already moving downward before the combustion force fully develops. Engines come in different cylinder configurations, and those configurations affect power delivery, smoothness, size, weight, and sound. The layout refers to how the cylinders are physically arranged. Inline, I or L. All cylinders are in a single straight row. Inline 4, I4, is the most common engine configuration in the world. It's compact, efficient, and cheap to manufacture. Inline 6, I6, is inherently smooth because its firing order naturally balances the forces, which is why BMW has made it a signature. Inline engines are narrow, which makes them easy to fit in an engine bay, but they're long, which can be a packaging challenge in some vehicles. The configuration. The cylinders are split into two banks arranged in a V shape, typically at 60 or 90 degrees. The 6 and V8 engines are shorter than inline equivalents, which makes them easier to fit in front-engine, rear-wheel drive layouts. The V8 is the icon of American muscle, 8 cylinders in 2 banks of 4, producing power and a distinctive sound that comes from the cross-plane crankshaft firing order unique to most American V8s. The burble, the rumble, the thunder at idle, that's a function of the V8's specific firing sequence and exhaust pulse spacing. Flat, boxer. The cylinders are arranged horizontally, opposing each other on either side of the crankshaft. Subaru and Porsche are the most famous users of boxer engines. The design has a naturally low center of gravity because the engine sits flat, which benefits handling. Boxer engines also have inherent balance advantages in certain configurations. The trademark boxer rumble from older Subarus comes from the unequal length exhaust headers that were traditionally used with the layout, not from the engine design itself. Rotary, Wankel, not a piston engine at all. Instead of pistons moving up and down, a triangular rotor spins inside an oval-shaped housing, creating intake, compression, combustion, and exhaust phases as it rotates. Mazda is the only manufacturer that has successfully mass-produced rotary engines for cars. They're compact, high-revving, and smooth, but they have drawbacks: higher oil consumption, seal wear, and emissions challenges. The rotary is a fascinating outlier in engine design that has a cult following precisely because it's so different from everything else. The number of cylinders and the layout affect the engine's character. A four-cylinder has a different sound, vibration pattern, and power delivery than a V6. A V6 feels different from a V8. A flat 4 feels different from an inline 4. These differences aren't just spec sheet numbers, they're part of the sensory experience of driving. The engine's layout is its personality. The engine needs a precise mixture of fuel and air to operate efficiently. Too much fuel and not enough air, running rich, wastes gas, fouls spark plugs, and increases emissions. Too much air and not enough fuel, running lean, generates excess heat, can cause knock, and risks engine damage. The engine's computer continuously adjusts the ratio to keep it as close to the ideal stoichiometric ratio as possible, roughly 14.7 parts air to 1 part fuel by weight. Modern engines use fuel injection, small electronically controlled nozzles called fuel injectors that spray precisely metered amounts of fuel either into the intake port or directly into the combustion chamber. There are two main types. Port fuel injection, PFI, sprays fuel into the intake port, just upstream of the intake valve. The fuel mixes with air in the port and enters the cylinder as the intake valve opens. PFI is simple, reliable, and proven. Most engines built from the late 1980s through the 2010s use port injection. Direct injection, DI, sprays fuel directly into the combustion chamber at very high pressure. This allows more precise control of fuel delivery and timing, enables higher compression ratios for better efficiency, and can improve power output. Direct injection is the current standard in most new engines. The downside is that because the fuel doesn't wash over the intake valves as it does with port injection, carbon deposits can build up on the valves over time, which can affect performance and require periodic cleaning. Some modern engines use a combination of both port and direct injection to get the benefits of each. Before fuel injection, cars used carburetors, mechanical devices that mixed fuel and air using a Venturi effect, and delivered the mixture to all cylinders through a common intake manifold. Carburetors were simpler and cheaper, but far less precise. They couldn't adjust the fuel mixture in real time. They struggled with altitude changes, temperature extremes, and varying loads. Fuel injection replaced carburetors because computers can manage the fuel-air ratio with a precision that mechanical devices simply can't match. Everything in the engine has to happen in the right order at the right time. Valves opening and closing, spark plugs firing, fuel injectors spraying, pistons going up and down. If any of these events are out of sync, the engine runs poorly or destroys itself. The timing system keeps everything coordinated. The crankshaft, which is turned by the pistons, drives the camshaft through a timing chain or timing belt. The chain or belt ensures that the camshaft rotates at exactly half the speed of the crankshaft. Because in a four-stroke engine, the valves need to complete one full open-close cycle for every 2 crankshaft rotations. Timing chains are metal roller chains, similar to a bicycle chain. They're durable, long-lasting, and generally don't need replacement within a typical engine's lifespan. They can stretch over very high mileage, which affects valve timing precision, but they rarely break outright. Timing belts are reinforced rubber belts. They're quieter than chains and cheaper to manufacture, but they have a finite lifespan. Most timing belts need replacement every 60,000 to 100,000 miles, depending on the manufacturer's specification. If a timing belt breaks while the engine is running, the camshaft stops turning. The valves stop moving. But the crankshaft, driven by the engine's momentum, keeps spinning for a moment. In an interference engine, where the valves and pistons occupy the same space at different times, a broken timing belt means the pistons slam into the open valves. This bends the valves, can damage the pistons, and often requires a complete engine rebuild or replacement. A $100 belt replacement on schedule prevents a $5,000 catastrophe. If your car has a timing belt, know the replacement interval and don't push it. Modern engines also use variable valve timing systems that can adjust when the valves open and close based on engine speed and load. At low RPM, the valves open gently and briefly for smooth idle and fuel economy. At high RPM, the valves open wider and longer to let more air in for more power. Honda's VTEC, Toyota's VVTi, BMW's VNOs, these are all brand names for variable valve timing systems that optimize the engine's breathing across the entire RPM range. Combustion generates extreme heat. Temperatures inside the combustion chamber during the power stroke can exceed 2,000 degrees Fahrenheit. If that heat isn't managed, it warps components, degrades lubricants, and eventually destroys the engine from the inside out. The cooling system circulates liquid coolant, a mixture of water and ethylene glycol, through passages in the engine block and cylinder head. The coolant absorbs heat from the metal surfaces, then flows to the radiator at the front of the car, where airflow carries the heat away. The cooled fluid returns to the engine to absorb more heat. A thermostat regulates this flow, staying closed to let the engine warm up quickly, then opening to allow full circulation once operating temperatures reach. If the cooling system fails, a hose bursts, the water pump breaks, the radiator clogs, or the coolant leaks out, the engine overheats. An overheated engine can warp the cylinder head, blow the head gasket, crack the block, or seize completely. Overheating is one of the fastest ways to total an engine, and it's almost always preventable with basic coolant maintenance and attention to the temperature gauge. Inside the engine, metal parts move against other metal parts at high speeds and under enormous pressures. Without lubrication, the friction between these surfaces would generate so much heat that the metals would weld themselves together within minutes. That's called a seizure, and it's exactly as catastrophic as it sounds. Engine oil creates a thin film between moving surfaces that prevents direct metal-to-metal contact. It reduces friction, absorbs heat, carries away contaminants, and cushions the impact loads on bearings and journals. The oil is pumped from the oil pan at the bottom of the engine through a filter and into a network of passages, called galleries, that deliver it to every critical moving component: crankshaft bearings, connecting rod bearings, camshaft journals, valve train components, piston rings, and the timing chain or belt tensioner. Oil degrades over time. The chemical additives that give it its protective properties get consumed. The oil picks up contaminants, combustion byproducts, microscopic metal shavings, moisture. It gets thinner or thicker depending on conditions. Eventually, it can't do its job effectively. That's why you change it. Regular oil changes, using the correct weight and type for your engine, are the single most important maintenance action you can take to extend engine life. Neglecting oil changes is the #1 preventable cause of premature engine failure. A $60 oil change protects a $7,000 engine. The math is not complicated. Every engine has a lifespan. With perfect maintenance and gentle driving, modern engines can last 200,000 to 300,000 miles or more, but they all wear out eventually. Here's what's happening over those miles. Piston rings gradually wear against the cylinder walls. As they thin, they seal less effectively. Combustion gases leak past the rings, called blow-by, reducing power and increasing oil consumption. The cylinders themselves wear, developing a slight taper or out-of-round condition that further reduces ring sealing. Bearings, the precision-fit surfaces that support the crankshaft and connecting rods, gradually wear, increasing clearances and reducing oil film stability. Valve guides and valve seats wear, allowing oil to seep into the combustion chamber and reducing sealing. None of this happens suddenly. It's a gradual, cumulative process that unfolds over tens of thousands of miles. The engine slowly makes less power, burns more oil, runs a little rougher, and becomes less efficient. Eventually, the wear reaches a point where performance is noticeably degraded or a component fails outright. A bearing spins, a ring breaks, a valve drops, and the engine needs a rebuild or replacement. Thermal cycling accelerates wear. Every time you start the engine cold and bring it to operating temperature, every metal component expands. Every time you shut it off and let it cool, everything contracts. This expansion and contraction, thousands of cycles over the engine's life, fatigues gaskets, loosens fits, and stresses materials. Short trips are particularly hard on engines because the engine never fully reaches operating temperature, which means moisture and fuel contaminants in the oil never fully evaporate. Those contaminants degrade the oil faster and promote sludge formation. The beautiful thing about engines is that the actions required to maximize their lifespan are simple, cheap, and accessible to everyone. Change the oil on schedule. This is number one. Non-negotiable. Use the correct weight and type specified in your owner's manual. Don't skip changes. Don't extend intervals beyond what the manufacturer recommends. The oil is the lifeblood. Treat it that way. Maintain the cooling system. Check coolant levels periodically. Service the coolant at the recommended interval. Watch the temperature gauge. If it starts climbing above normal, stop driving immediately and investigate. Overheating kills engines fast. Don't ignore the timing belt. If your car has one, check your manual. Replace it at the specified interval. No exceptions. A broken timing belt on an interference engine is a catastrophe. Warm up gently. You don't need to idle for 10 minutes on a cold morning. That's a myth from the carburetor era, but you should drive gently for the first few minutes, keeping RPMs moderate until the engine reaches operating temperature. This allows the oil to warm up, flow properly, and reach all critical surfaces before you demand full performance. Don't lug the engine. Lugging means driving at low RPM under high load, like going uphill in too high a gear. It puts extreme stress on bearings and the timing system. If the engine sounds strained, downshift. Listen to it. Your engine communicates through sound. A healthy engine has a consistent, smooth note. New noises, ticking, knocking, grinding, whining, are symptoms. A ticking at startup that goes away might be a lifter bleed down, which is usually minor. A persistent knock under load could be detonation or a failing bearing, which is serious. A grinding sound on startup could be a failing starter or timing chain tensioner. Learn what your engine sounds like when it's healthy, and you'll notice instantly when something changes. That awareness alone can save you from a catastrophic failure, because the difference between a $200 repair and a $7,000 engine replacement is often just a few weeks of ignored warning sounds. Modern engines are managed by an electronic control unit, the ECU, also called the PCM, Powertrain Control Module. This is a small but incredibly powerful computer that receives input from dozens of sensors throughout the engine and makes real-time decisions about fuel delivery, ignition timing, valve timing, idle speed, emissions controls, and more. The sensors feeding the ECU include the mass airflow sensor, measures how much air is entering the engine. The throttle position sensor measures how far you've pressed the gas pedal. Oxygen sensors in the exhaust measure the air-fuel ratio after combustion. The coolant temperature sensor, the intake air temperature sensor, the crankshaft position sensor tells the ECU exactly where each piston is in its cycle, and the camshaft position sensor tells the ECU where the valves are in their cycle. There are others, but these are the major players. The ECU takes all of this information, processes it against pre-programmed maps and algorithms, and adjusts the engine's operation continuously. It decides exactly how much fuel each injector sprays, exactly when each spark plug fires, and exactly where the variable valve timing system positions the camshafts, all updated dozens of times per second. If a sensor fails or sends incorrect data, the ECU detects the anomaly, stores a diagnostic trouble code, illuminates the check engine light, and often enters a limp mode that protects the engine by limiting power and RPM until the problem is fixed. Before electronic management, Engines relied on mechanical and vacuum-operated systems for fuel, metering, ignition timing, and emissions control. These systems worked. Cars drove fine for decades with carburetors and mechanical distributors, but they couldn't adapt in real time the way a computer can. A carbureted engine running at sea level would run rich at high altitude because the mechanical mixture adjustment couldn't compensate for the thinner air. A modern ECU adjusts automatically based on the mass airflow sensor reading. The computer made engines dramatically more efficient, more powerful, cleaner, and more reliable than their purely mechanical predecessors. After the combustion gases leave the cylinder through the exhaust valve, they enter the exhaust manifold, a set of pipes that collects exhaust from each cylinder and merges them into a single pipe or a pair of pipes. From there, the gases flow through the catalytic converter, which chemically converts toxic pollutants, carbon monoxide, unburned hydrocarbons, and nitrogen oxides into less harmful substances using precious metal catalysts. After the catalytic converter, the exhaust passes through a resonator and muffler, which reduce the noise of thousands of explosions per second to a socially acceptable level. Without a muffler, your engine would be deafeningly loud, which is why cars with deleted mufflers or damaged exhaust systems sound like they're broken. They are, in a regulatory and decibel sense. The exhaust system also houses the oxygen sensors that the ECU uses to monitor the air-fuel ratio. These sensors are critical for engine management. Without accurate oxygen sensor readings, the ECU can't properly adjust the fuel mixture, which leads to poor performance, increased emissions, and potential engine damage. Fix problems early. A small coolant leak becomes a blown head gasket. A rough idle becomes a destroyed catalytic converter. A ticking noise becomes a thrown rod. Engines give you warnings before they fail catastrophically. Pay attention to them. Your engine is a controlled explosion machine. 4 strokes: intake, compression, power, exhaust. Repeat thousands of times per minute in each cylinder. Pistons push connecting rods that turn the crankshaft, converting explosions into rotation. The block holds the cylinders. The head holds the valves and camshafts. The head gasket seals everything together. Fuel injection meters precise amounts of gasoline into the cylinders. The timing system keeps valves, spark, and pistons in perfect sync. A broken timing belt on an interference engine destroys everything. The cooling system prevents the engine from melting itself. The oil prevents it from grinding itself apart. Engines wear gradually over hundreds of thousands of miles through ring wear, bearing wear, and thermal cycling. Regular oil changes, coolant maintenance, and not ignoring warning signs are the difference between an engine that lasts 300,000 miles and one that dies at 100,000. Your engine isn't magic. It's mechanical. It's logical. It's a machine that converts fuel into motion through a sequence of events that hasn't fundamentally changed in over a century. The 4-stroke cycle: air in, compress, ignite, exhaust out. That's it. Everything else, the fuel injection, the variable valve timing, the computer management, is refinement of that basic idea. Understanding how it works doesn't make you a mechanic, but it makes you an owner who knows why maintenance matters, what the warning signs mean, and how to avoid the catastrophic failures that turn a running engine into a very expensive paperweight. That knowledge costs nothing. Ignoring it costs thousands. If this video finally made the engine click for you, pun absolutely intended, hit like. Drop your engine type in the comments so we can see how many inline 4s versus V8s are watching. And subscribe so the next time someone pops their hood and starts pointing at things, you can actually follow along instead of nodding politely and pretending you know what a camshaft is. Later.